Okay, class, in the last video, we had to split it up. What we were talking about is that the membrane, close to the membrane, has a net negative charge. Close to the membrane has a net positive charge. However, if we add up all the charges on the inside the cell, all the positive and negative, they come to zero, which we call book electron neutrality. If we add all the charges on the outside the cell, positive and negative, they come to zero, which we call book electron neutrality. Then the question is, how can you have a net positive close to the membrane on the outside and a net negative on the inside? And I'm saying that has to do with something we're going to call the dragging effect. The dragging effect. All right. Two things to know. That not all these ions can move through as easily. Chloride can move through the membrane the easiest. Potassium almost as easy as chloride. Sodium has a lot of difficulty getting through the membrane, and large molecular anions, the membrane is totally non-permeable to. Okay. Now, these ions, through their passive leak channels, would like to reach equilibrium. Of course, we need to keep them at this equilibrium, as we'll see later, because if they reach equilibrium, you're dead. You have to keep them at this equilibrium. But they will try to leak in. All right. So now our subject is how net negative, how net positive, though everything is equal to zero. And we call this the dragging effect you can read on. All right. Sodium wishes to enter the cell by according to the electrochemical gradient, by charge, because sodium is positive, inside negative, by concentration. Sodium is high concentration outside, low inside. Okay? So sodium with this strong driving force would like to come in, and it will try to push in through its leaky channel. However, the problem with sodium coming in is that it would add an extra positive charge to the inside, which would violate book electron neutrality. Then you'd have more positive than negative. So for sodium to come in, it has to pick a negatively charged ion that wouldn't mind coming in also. That could be chloride. Chloride's higher outside than inside. Now, however, chloride is a little hesitant to go in some ways on the charge because it's negative, inside's negative. But still, the diffusion gradient is a little greater than the charge gradient, so it'd like to come in. So sodium negotiates with chloride to come in. They both hit the door. Here's the problem. Chloride can easily go through. Sodium can't. So chloride gets halfway through. Think about it, halfway through, and it's having to drag sodium with it because sodium can't get in as fast. So the chloride is halfway in with its, let's say, its nose tipping the inside. Sodium squeezing, but its nose is still out here. As we'll say, its backside is still out here. So therefore, this sodium pressed hard against here, and this chloride pressed hard here, not getting through, gives a net negative here and net positive there. What then happens? Both finally pop through. But then in that same spot, another chloride and sodium come, and then another one, and then another one. But that's not just happening there. That's happening all over. So you see, you don't get through unless you bring the positive brings the negative. But in the interim while it's doing that, you have one nose pressed here and a backside pressed here, giving you a net negative, net positive. And that's what we'll call the dragging effect. Okay? Now, potassium has a moderate desire to move out because it's this and this. But for potassium to move out, it would have to bring the large molecular anions. And you can see the same thing would happen. The large molecular anions couldn't do it. They'd be trapped on the inside trying to squeeze through, and potassium would be almost out. So whether we speak of the sodium issue or the potassium, in both cases, it would line this membrane with a net positive on the outside, net negative on the inside, but all the charges inside would equal to 0 and all the charges outside would equal to 0. Okay. So that's what this whole portion is that you can read on. Okay. Now, let's get to something else. Since the ions can passively leak according to their gradients, if allowed enough time, each ion type would reach equilibrium and there would no longer be a resting membrane potential. So then the question is, what sustains the resting membrane potential? Okay, let's look at this. First, understand that if the resting membrane potentials on your cell membranes are lost, you would die. The resting membrane potential is very important for many, many functions. One function to be discussed in this document is the action potential of nerve and muscle, which will come up. An action potential is a moving potential, whereas the resting membrane is more of a static one. But you cannot move a charge without having a charge. You cannot move a charge without having a charge. So then you couldn't use the brain or anything else. All right. So what keeps them at disequilibrium? It's a necessity to keep them at disequilibrium. The two things that maintain the rest are the ATP-dependent sodium-potassium pump and those trapped large molecular anions. The ATP sodium-potassium pump and those trapped large molecular anions. Okay, let's move further. Let's start first with the intracellular trapped large molecular anions. Okay, now let me count. You can read this, but let me kind of get it. Okay. The large molecular anions, by them being trapped in here, but having a negative charge, but having a negative charge, this gives, then they are contributing some charges to book electroneutrality. All right? They're contributing some charges to book electroneutrality. Okay. Now, let's think about that. They are trapped. They cannot reach equilibrium under no circumstances. Therefore, even though more potassium would like to exit, see, it's in high concentration inside and outside, it cannot exit because it has to stay behind. Even though it's quite permeable and some would like to exit according to diffusion, it cannot do that. Why? Because it has to stay behind to add these positive charges to these negative. And since you cannot reach equilibrium, you have to stay behind and babysit me. The potassium has to stay behind and babysit this. It can't do what it wants to because it has to counteract the charges here. Likewise, chloride more would like to come in, but it's going to be difficult because you already got all these negatives in here that can't reach equilibrium. Okay? What does that mean? That means because of that, sodium can't come in if you can't bring chloride with it. So you see those large molecular anions do that. Now, in experimentation in some of the laboratories, if you were to take the large molecular anions out, which it has been done experimentally, the resting membrane potential is gone immediately. The resting membrane potential. So really, this is the big one, is this. Even though the book is going to bring up the sodium-potassium pump, which I'm going to get to right now, but really the large molecular anions are the big ones. Now we're coming to what does the sodium-potassium pump do? The sodium-potassium pump depends on ATP, and it's a pump. Anytime you hear the term pump, you mean active transport. That's where this energy is coming from, this ATP. All right, the way the pump works, this transmembrane integral protein pump pumps 3 sodiums out. Now remember, sodium is already high outside. So it had to push from low concentration into high. It had to push from low concentration into high. And at the same time in that pump, it's pushing 2 potassiums in. Now remember, potassium is already high inside. So what it's essentially doing is restoring potassium to the inside that has leaked out. Restoring potassium to the inside that has leaked out. And restoring sodium to the outside that has leaked in. So it's a combination then. If you look at it, you say, well, which is the most important? Well, actually both. This is more of a spring cleaner because the large molecular anions will make it go away quick. Now, if we were to poison means to put a chemical to turn off the pump for a moment, then the resting membrane potential would gradually go down over a few hours. But if we take those molecular anions out, hey, it's gone immediately. So both are really working together. Both are working together. So that's how we maintain that RMP even though the things leak. Let's go to something else. How do we measure the magnitude of the resting membrane potential? See those numbers up there? How do we measure that? Okay. The way this is measured basically is this. I'm going to use this as an example right here. We're going to make an electrode. Okay, this is how the electrode would go. An electrode is a glass pipette with a solution in it, an electrolyte solution. Remember, the membrane here acted as a resistor. So the electrode, this setup is going to override the resistor. It's going to allow the current not to have to travel through the membrane. So I'm going to put a pipette out here, an electrode, glass rod with electrolyte solution, put a copper, a silver, a gold wire in here, hook this to a voltmeter. Now what we're looking at, the force of movement of a charge. The force of movement of a charge. Force of movement of a charge is measured in volts. You can read that in my document here. Force of charge. I'm going to take another pipette. Now they're not showing the pipette, but I'm going to take another electrode and put it out here. Another electrode and put it out here, which would look just like this one. All right. Now we come to, okay, now, so that means the charges here would go out in the inside, go into here, hit here, push in here, and however much push it was would be measured in volts and then come out here. So we're bypassing this. We're bypassing this. And this is measuring the force. Now, these little cells here do not have enough force and push to equal 1 volt. They not even close to 1 volt. They equal thousands of volts. So instead of I'll come over here. Instead of doing something like this, let's say 0.070 volt, which is what it would be. Let's do it this way. Instead of having to use a decimal point in front of volts, let's just do it this way. Let's just say, make it in thousands and say 70 and reflect it in the units, millivolts. See what I did? 0.070 volt equals to 70 millivolts. Okay. So we can do it that way. That's a better way, and you don't have to deal with the thousands issue. Okay? Now, by international agreement, listen to me, by international agreement, the measurement occurs from the inside electrode. The outside is considered the ground electrode. Since the inside of the cell is negative, close to the membrane, then that's where you get the number of negative 70 millivolts. So in this neuron, the resting membrane potential would be a negative 70 millivolts based upon how I described it. Now, different cells have different resting membrane potentials. For example, muscle cells have about a negative 90. So we have now measured the magnitude of that. Okay, and that's where we are. Each cell type has a different. For example, the neuron is a negative 70, which this is, but the muscle about a negative 90. All right, so now we're through with resting membrane potential and we're ready for neuron action potential. All right, so we'll close here.